We'll get started here in just a minute. All right, good afternoon, everyone. It's 101, so I think we should get started today. We're doing a quiz to start. We're going to finish 1.4. We're going to start 1.6. We're going to skip 1.5. I will explain that when we get to it. Next week, 1.6 is pretty long, so we're going to have to take time next week to finish out 1.6. And then a reminder that your homework for 1.3 and 1.4 is due on Sunday night. And what else? Exams kind of ways off, and then your camera thing. Questions before we begin?
For the homework, is it just the problems you assigned, or is it everything that's on the syllabus?
Well, if I just say to do a certain set of problems in class, like let's say, hey, on this, just do this, then that's all you have to worry about.
Okay, sounds
Yeah,
good.
and remember, the homework is always just, the only reason I'm having you submit it is just to get you used to like writing down stuff and getting used to seeing your style, like, you know, how neat you are, how organized you are, how your notation looks. I'm not really like, oh, you know, Red skipped 2 problems. You know, it's not what it's about. It's about, you know, are you putting in honest effort to the class? So as long as you don't have to get every single problem done, just, you know, to a point that I feel like you've done enough to be ready to continue moving. Anything else? All right, let's do it. First quiz. So I'm going to launch a poll. It's 2 questions, multiple choice. Your exams are not going to be multiple choice. Like there will be no multiple choice at all. So it's just easy for me to do it this way. So here we go. It's 2 questions. I hope it's big enough. I am not going to ask you to submit any work to me. This is just give me your answers, A, B, C, or D for each one of these 2 problems. All right, there's 2 limits. All right, let's get going. I'll determine how much time you have based upon how many responses I'm getting. So I can say I don't think we're going to go more than 10 minutes. I think 10 minutes would be the absolute max I would go on this. So see how it goes. We're 6 minutes in. We have 6 people who have responded to both questions. If the poll is not coming up for you, just send me a chat that has your answers. We're going to go 1 more minute. Ten seconds. Okay, I'm closing the poll. 3, 2, 1. All right. Okay, so I just shared the poll results to you, or with you, I should say. And hey, look, remember what I said last class about no matter how much I stress it, somebody is going to put 0 over 0 undefined, right? And I said, maybe not this class. Well, we had 2 people answer A for the first one, and we had 4 people answer A for the second one, which I said in class last time, I would give you how much partial credit for that? Nothing. Okay. A complete. Now, I'm not trying to humiliate the people who did that. I'm trying to say this so you don't do this on the test. If it were as easy as just identifying that you get 0 over 0, then calculus, I mean, it's the whole point of calculus is that that's not the answer, right? So I'm gonna say it again, right? Should not be 0 over 0. Now, looks like the rest for number 1 was C, 7/6. That is correct. And for 2, the majority of you selected B, -1/4, and that is correct. So let's just work through these, all right? I won't always be able to work through the quizzes just for time's sake, but I will do it for this first one. So what we do here is, of course, the first thing we do, and I think Red was the one who said this last time, you always start a limit by just replacing all your X's with the number, right? And plug in and see what happens. And when we get this, we get 0 over 0, right? And we know that that means we have to do something, right? Like we actually have to do some algebra or some sort of trick. So the algebra that's involved here is just the algebra involved here is just factoring the numerator and denominator. So you have to factor the numerator to be x plus 4 times x minus 3. and then factoring the denominator to be difference of squares, x plus 3 times x minus 3. Your x minus 3 factors cancel, and now you're taking the limit as x approaches 3 of x plus 4 over x plus 3. And if you replace the x's with 3's, you get 7 over 6, and that's your answer. That's the first one. Now, the second one, when you do the direct substitution of 4 into here, you get 0 over 0 again. All right, so because you get 0 over 0, now we need to do some algebra. And the correct algebra here would be to recognize that you have that square root. And then from class yesterday or the other day, we said that when you see square roots, you start maybe thinking about conjugates. So you can bring your conjugate in here on the top and bottom. And then you do your foiling out and figure out what happens. So here to here is 4. The middle terms will cancel, guaranteed. And then your last terms here to here, you get minus x. So everything on the top is gone, except it's turned into 4 minus x. And on the bottom, we recognize now that 4 minus x is very close to x minus 4. They're off by a sign. So this is where we talked about last time again, that when they're off by a sign, what you do is you rewrite this, but you pull a -1 out. And when you pull a -1 out, now this expression, -4 plus x, is the same as x minus 4. And now these will cancel. So what you're left with is a -1 on top. And then on the bottom, you still have this 2 plus root x. And then you're still taking the limit here as x goes to 4. And now when you do it, you'll get it, square root of 4 here is 2. So you get -1 over 2 plus 2. And that's -1/4. Okay, questions? We're good. Okay. I'm going to do 2 more examples, continuing what we were doing last time, just to kind of get us going here. And then we're going to move on to the second part of this section. There's more, well, another part of this section. So here's a limit. We want to take the limit as h approaches 0. As h approaches 0 of this expression. So I think this might be the first time that we've had a limit where we've got like 2 variables in here, right? The h is the thing that's going to 0. So this h and that h are going to 0, but we still have these other 2 variables, or this other variable within the problem, all right? So let's just see what happens. If we let h go to 0, let's see what would happen up top. If we let this go to 0, all you'd have there is an x plus 3, right? Or sorry, x plus 3, x cubed, x plus nothing is x and then cubed. Then we subtract from that x cubed, that's this. And then we're dividing that by h, but h went to 0, so that's 0. And x cubed minus x cubed is 0, so 0 over 0, and this is bad, right? So we have a problem. So since we have a problem, I'm going to now try and do some algebra. Why am I zoomed in so much? There we go. So now I'm going to try and do some algebra. So limit h goes to 0. Okay, I have x plus h cubed minus x cubed over h. Anybody see anything they want to do here?
Difference of cubes.
Okay, so you see a difference of cubes. Okay, so that would be, so remember what I said last time, there are certain things we want to be looking for, right? Difference of squares, difference of cubes, conjugate, combining. If we have complex fractions, we do like a common denominator. But at the end of the day, any algebra that's legal, you can try, okay? So as long as it's legal, like you're gonna go somewhere. It's just important to understand that it may not be the right way. Let's see what happens here. I'm being told difference of cubes. So I think what's being noticed here is that we can look at this as almost being like, oops, let me use a different color. Almost like this is like a cubed minus like b cubed. So I could do like a difference of cubes formula for that. Do y'all agree? I could do that. Now the formula we talked about this last class, a cubed minus b cubed would be a minus b times a squared plus ab plus b squared. That's the formula for difference of cubes. On your formula sheet, they use x and y. They don't use a and b, but you could replace x and y with a and b, and it's the same thing, right? So for us, if we're going to do this, who suggested this? Was that you, Ash?
Yes.
Okay, so Ash suggested this. So if we do this, this right here, the x plus h is really like our a, isn't it? That's what our a is here. It's the thing that's been cubed.
Yes.
And then we subtract from that the x, which is like our b, yeah?
Correct.
So let's do it. We're gonna have the a, which is x plus h. We're subtracting from it the b, which is the x. And then in parentheses, we're gonna have the a squared. Ooh. Well, a is x plus h, so I'd have to write x plus h squared. And then plus the a, which is the x plus h, times the b, which is x, and then plus the b squared, which is x squared. Oh, this is looking terrible. Does everyone follow what I did though? As far as just like plugging things in and replacing? Are there any questions on that? As bad as this looks, do y'all see this works? You see what happens out here in this first parenthesis? Do you see if the x's go away? And all this really is an h out here. And then that h will actually cancel with the h on the bottom. And so all we're left with is limit h goes to 0, and then all that crap that was in this parenthesis. So I'm just gonna write out x plus h squared plus x plus h times x plus x squared. Okay, that's all that's left, right? And we're gonna let h go to 0 now. Okay, so I'm ready to now let h go to 0 and see what happens. Well, if I let h go to 0, that goes away, and that goes away, right? So it's like all this first term becomes is x squared. Notice no more limit, right? I'm letting h go to 0. Then I have, this is just x, and then times another x, so that'll be plus another x squared, and then plus another x squared. So I get at the end of this 3x squared. I believe this is the first limit that we've done together in class where our answer actually has a variable in it. Every other problem we've done, the answer has been a numerical value. So this just goes to show you that if you take the limit of an expression and you get 0 over 0, it is possible that if you have more than one variable in here, that you could get an answer that contains a variable. All right. So Ash suggested, it's hard to say, that we do difference of cubes. And it worked, right? It worked. Does somebody have another algebra approach that maybe would work? Anyone have another idea of what we could do other than using this difference of cubes?
We use the binomial theorem.
Okay, so you're saying like take the x plus h cubed, and why don't we just figure out what x plus h cubed is? Like, let's do that. Let's just do over here. What's x plus h times x plus h times x plus h? Like, let's expand that. Okay, that's the way we would say that mathematically. Let's expand that expression. So if I were expanding this, the way I would do it is I would multiply those two together first. So I'd do a little like, you know, this thing. I'm not going to show the work, but that would come out to be x squared plus 2xh plus h squared. And then I would have to multiply again. So I'd have to do the x through and then the h through. And if you do all that algebra, again, I'm not going to show all the work. You get x cubed plus 3x squared h plus 3xh squared plus h cubed. I'll revisit this later, okay? There's a shortcut for this, but I'm not going to talk about it right now. This is what you get when you expand that out. So algebraically, that's the same thing. So I could, if I wanted to, rewrite this as limit h goes to 0, and then everything in yellow here is going to be replaced with everything in yellow there. So it's x cubed plus 3x squared h plus 3x squared plus h cubed. That's everything in yellow. But then I still have, don't forget, minus x cubed. So I have to take away from that minus x cubed. And then everything there is divided by h. If we do that, this x cubed and that x cubed go away. And then there's something pretty nice here. Do you all see it? Bellum, I see you shaking your head. Yes, what do you see?
I was just like hearing you, but I'm really nerdy.
I'm sorry.
Maybe that, like the 3x cube h plus 3h, like h cube, no, h squared are similar.
What do all of these, Bellum, what do all of these have in common?
The
What do they all
h.
have? They all have an h, don't they?
You can
all
like
have an
divide each one.
We could divide, I'm going to do it a little different. I'm going to say, let's factor an h out of the top. Just a single h from each one of those.
Oh, common factor. Yep.
Yeah, just a common factor, exactly. And then the good thing about that is if we do that, the h is now canceled, right?
Mhm.
And so where we are now is the limit h goes to 0 of 3x squared plus 3xh plus h squared. And now let h go to 0. Okay, now that we've gotten rid of the bad part, right? That bad part, the h on the bottom, let's now let h go to 0. And when we do that, this one goes to 0, which basically kills all of that.
0. Mhm.
0 here, it's gone. And the only thing left is 3x squared, which doesn't have an h in it. So that's just 3x squared. And that's the same answer. And it's not a coincidence. It just so happened that on this problem, 2 different algebraic approaches give us the same result. All right. So there's never like you have to go down this path, which is kind of makes this challenging, right? Because there's not like, oh, every time I see this, I do this. You kind of have some freedom to kind of drift and get lost, which happens. Okay, questions there? Comments, concerns, complaints?
Is there a preferred way that you have for us to do it, or either of these will work for the exam?
You get 3x squared, I'm happy.
Okay.
Both of these algebraic techniques are, I think, similar in terms of difficulty. I mean, this understanding how to rewrite this as a difference of cubes correctly, I think requires an understanding of the difference of cubes. And then being able to expand x plus h, right, and cube and do that algebraically requires some thinking. So I think they're both about the same. I have no preference.
Thank you.
So just
Okay.
a little detail. Always we put like the equal sign before the limit, right? Like we cannot put like limit and then equal the equation.
Yeah, like this would, okay, so if you wrote this, limit h goes to 0, 3x squared, and you say that's your answer, is that what you're saying?
Yes.
Yeah, so I'll tell you this, that technically is still correct.
Okay.
Okay, but you've already taken the limit, right? You've already let h go to 0. So h is no longer playing a role in this at all. So it's kind of like you don't need that, you know? Just remember, you dump the limit after you let the variable go to what it's supposed to go to. That's when you dump the limit. That's when you stop writing it. But up until that point, it's got to be sitting out there in the front the whole time.
All right. Thank you.
Yep. All right, let's do another one. You know what? I think, well, yeah, I'll do it. All right, I'll do it. Give me a second. I gotta turn my heater off. It's really hot. All right. It was cold and then it was hot. All right, here we go. All right, this one. First step, let x go to 4. Let's see what happens. So if you put 4 into the numerator, you get 0. Then on the bottom, 4 squared is 25. If I add 9, I get what? Wait a minute, hold on. It's not 4 squared, it's not 25. 4 squared is 16. And then when I add 9, I get 25, sorry. Right, so that's 25. Square root of 25 is 5. So we get 5 minus 5 is 0. It's funny because I sit here and I'm writing on the screen that's in front of me and I look up and I can see everyone's video on, which I'm very happy to see. But it's funny because Nico, your camera it's just an image of you and it looks like you're so happy. Every time I look up, Nico looks so happy. Can y'all see Nico? Just a still image of Nico looks really just like he's enjoying this quite a bit. Okay. So 0 to 0 bad, we need algebra. Anybody have an idea of the algebra here?
We could get the conjugate first to get rid of it, and then
You
after
want to do
the
the conjugate?
yeah, we can do the conjugate, and then we can factor out the x squared plus 9 afterwards. No?
Okay, so conjugate, let's bring it in. How do you want me to bring it in? You want me to multiply this, right?
Mm-hmm.
Top and bottom by the conjugate of the bottom. What is the conjugate of the bottom?
X plus square root of x squared plus 9.
5, you said x. 5.
Yeah, 5, yes, sorry.
5 plus the square. That's all right, I understood. That, and then same thing on top. Now, why is Robert doing this? Because I've kind of told you already, if you see square roots, conjugate's kind of like a good way to go, right? Like go try this, right? So that's what we're going to try. There's no guarantee this is going to work. We're going to cross our fingers, hope for the best. So let's do the multiplication on the bottom, because that's where things are going to get interesting, right here. So when we do the first multiplication here, let me go ahead and rewrite the limit. Limit x approaches 4. Okay, my new denominator is going to be 5 times 5, that's 25. And then the middle 2, I don't need to worry about, right? Because they'll cancel each other out, guaranteed, which is the reason we do it. The last terms together, you have to be careful with, all right? And the way I think about it is we're multiplying a negative times a positive. So I know my answer is going to be negative, so I put minus. And then I'm doing a root times itself, right? Root x squared plus 9 times root x squared plus 9. The root should go away, and I should get x squared plus 9. The important thing to remember, though, is that that minus sign has to distribute to both of those terms, which means you have to have this in parentheses. And if you forget that, or if you don't do that, you're never going to get this to work out properly. So you have to understand how that algebra works. And then in the numerator, I'm actually not going to touch anything. I'm going to leave the 4 minus x there. And I'm going to leave the 5 plus the square root of 20 of x squared plus 9 in there. I'm going to leave it. I might have to multiply it out, but I'm just going to leave it for now. And let's see what happens on the bottom here when we distribute this through.
Will it become negative?
Yeah, so copy, I get to cheat here and copy and paste this here. So this becomes, if we distribute, this becomes a minus x squared and then a minus 9, right? That. And then now that just becomes 16 minus x squared. All right, let's call on some people here. And you know what? Since Nico looks so happy, Nico, you see what we can do here?
We could just take the denominator and make it into 2 parts.
Yeah, right. Nico sees this is a difference of squares, right? 16 minus x squared is 4 plus x, 4 minus x. And you can kind of see how that's going to cancel, right? You see that?
Mm-hmm. Yes.
Good. So 4 minus x, and then 5 plus square root x squared plus 9. I realize this is a lot of writing, but you know, hey, it is what it is. 4 plus x, 4 minus x. That's your difference of squares for the denominator.
And you're gonna cancel.
Cancel
Yeah.
these factors.
Yeah.
There we go. And now you've actually eliminated the part that's causing the division by 0, right? This term right, or that factor, that's the part that caused division by 0, because when I try and put 4 in there, I'd get 0 on the bottom. But now we've canceled it out. So we shouldn't have a problem anymore, which means we should be ready to let the x go to 4 now. So let's let it go. And I'm no longer going to write the limit. So if x goes to 4 in the numerator, I get 5 plus square root 4 squared plus 9 over, and in the denominator I have 4 plus x, so 4 plus 4. So 5 plus, we already said that this was 25 and the square root of 25 was 5. And on the bottom we get 8. So you should get 10 over 8, which is 5/4. 5/4. All right. I hope that you were able to get through a lot of that homework, and that doing all this, you kind of get a feel for some of the algebra that's involved, and that you feel somewhat comfortable with it. We need to move on. All right. We're going to just keep cruising along here. We got to move on to the next part of this section and then get into 1.6. So without further ado, let's move on in this section. We now have two very important limits. All right. These are limits that you need to just know what they are. All right. So the first one, I'm going to write it over here to the side. Limit x approaches 0 of sine of x over x equals 1. Okay, you need to just know that that's the answer, right? Right now, where we are in this class, I have no way of proving that that answer is 1 algebraically. Okay, I cannot prove that to you. There's no, you know how, well, let me back up. If we try and let x go to 0, maybe I should have done this first. If x goes to 0, the top goes to sine of 0, and the bottom goes to 0. And sine of 0 from pre-cal, we all know, yeah, do we all know, is 0. And 0 over 0, that would be bad. Okay, so this is where we would normally say, oh, we need some algebra, some trick. And I'm telling you right now, there is no algebra and there is no trick that you're going to be able to do to get this to work out. All right, there's nothing you can do to show me that that's 1. And in fact, there's nothing I can do to show you it's 1 either. Well, I can, but it's a whole different thing, and it's not within the scope of this class. All right, there's a way I can show this to you. I can prove it to you, but it's a geometric proof. It's beautiful. I'm willing to share it with you during my office hours, not here. So you're just gonna have to take this on faith. All right, you're just gonna have to take it on faith that that's it. Now, later on in this class, I will be able to prove it to you, but I have to put some more tools in your toolbox first, and then we can use those tools to prove this is true. So for now, that's something you'll take on faith. Now we can kind of like verify it if you wanted. We could graph sine of x over x. There's the graph of the function sine of x over x. Let me do something here. Yeah, that's what this graph looks like. All right. And so our question is, what is the limit as x goes to 0? Let me zoom in. So we're saying if you were to start approaching 0 on the x-axis, that means you're walking along this function. I hope you can tell that from the left and from the right, it looks like we're approaching that value of 1 up there, right? From both sides, that's what it looks like we're doing. But like I said last class, there's kind of a problem with these computers is that they don't show you the hole, right? There's an actual hole up there. I was saying that, and then the other day, yesterday, I went and if you click on it and drag your mouse, watch what happens when I get to the top. Well, will it do it? Oh, come on, you got to do that for me. It's not doing it. Let me make this smaller and zoom in. Okay, if I click and drag, see if I, oh, there we go. See that? Look, it says it's 0, it's undefined, right? And it actually has a little hole there. You can kind of see it. But it would be nice if they just put that hole there, right? Be nice if they had that sitting there like that, then we would know there's a hole. So we know that when you try and plug 0 into this, when you try and plug 0 into it's undefined, right? 0 over 0 is bad. We're saying what happens is you approach it from both sides. The answer is 1. You take it on faith, okay? The other thing to know is that if you flip it over and do it the other way around and put the X on top and the sign on the bottom, you actually get the exact same answer. So I'll do that. I'll prove that to you. If I do X divided by sine X, there's the graph of X divided by sine X. And you can kind of see, again, that it is from the left and from the right approaching 1. All right, so it doesn't matter if you flip it over. That's the first one you have to know, you have to memorize. And then the second one isn't used as much, but you should know that it is this limit. And that is, if you let X approach 0 on cosine X minus 1 over X, see what happens. So if you plug in 0 for X, you get cosine of 0 minus 1 over 0 on the bottom. And cosine of 0 from pre-cal, cosine of 0 is 1. So you get 1 minus 1 over 0. That's 0 over 0. That's bad. We need to do some algebra. There is no algebra I can show you. Sorry. You have to take it on faith. The answer to this is 0. All right. You got it. Now it's your job to burn those into your mind. All right. Now that's the way the book presents this idea of these two limits. All right. I have a slightly different way I want you to look at it. All right. Here's the way I want you to look at it. And I'm only going to talk about that first one. With this one right here, the way I want you to think about this is this, that essentially we have a limit, right? And in this case, X, I want you to just not care what it's going to, okay? Don't worry about it. Don't worry about whether or not it's going to 0 or anything else. Just ignore that for a second. Here's what I want you to think about. If you ever see this sign, and inside of this, you have something, all right? I don't know what it is. It's something, I'm just going to call it junk, all right? Junk, whatever it is, it's just some junk sitting inside the sign function. And then on the bottom, you have the exact same junk sitting down here, all right? Here's what I want you to know. This limit will always be equal to 1. It will always be equal to 1, so long as these two conditions are met. If first, the junk on the top equals the junk on the bottom. That means that whatever's sitting inside of this sign right here must be exactly the same as what's down here. So as long as these two things match exactly, first, and second, the junk is headed to 0, all right? As long as the junk matches and as long as the junk is headed to 0, then you can tell me that the answer is 1. Let me show you an example of what I'm trying to illustrate here. As an example, if you want to take the limit as X approaches 2 of sine of X minus 2 over X minus 2, my answer here is 1. Now, the reason why it's 1 is because I looked at it and said, okay, I had sine of some junk over some junk. That was an exact match, right? X minus 2 is equal to X minus 2. They're exactly the same things. And when I let X go to 2, this goes to 0, that goes to 0, right? They both are headed to 0. So as long as those two conditions were met, that they matched and they both went to 0, then the answer is 1. All right, that's the way I prefer that you learn it. And also keep in mind that this can be flipped over. So if you had the junk on top and the sign of the junk on the bottom, then it's still going to give you 1. All right? You with me? You sure?
Can you please revisit what you mean by if it was flipped over?
Okay, so just if this was limit x goes to who cares of junk over sign of junk, that'll be 1. So if you flip it over and you have the junk on top and on the bottom, it's the sign of the junk, you still get 1 so long as you still have to have these 2 conditions met. The junk has to match exactly, and it has to be going to 0. Does that address your question? Yes.
Yes, thank you.
Okay, so let's see if you really understand this. Limit x approaches 0, sine x over 4x. What's this limit? So first thing, like Red brought this up last class, right? What's the first thing you always do for every limit? Plug in the value, see what happens. So you plug in 0, sine of 0, we all need to know is 0. And then 4 times 0 is 0. So we have 0, 0. This is bad, right? We're supposed to do some algebra, but there is no algebra you're going to be able to do here. There's none. And please don't do this. Please, please, please don't cancel the x's. Please, please don't do that. Right? You can't do that. That x is trapped, right? This x is trapped in the sine function. We call it the argument of the sine function. The argument within a trig function cannot be played with like an algebraic factor. You can't do that, right? It's stuck in the function. So now we start thinking about the rule I just gave you, or the property I just gave you. If we have junk here, and the junk goes to 0 and they match exactly, the answer is 1, right? Do we have that though? They don't match, do they? Right? Like x here, that goes to 0, doesn't it? I mean, when x goes to 0, that goes to 0. So that goes 0, that's good that it goes 0, but it doesn't match this. These have to match exactly. Exactly, they have to match. And they don't. So watch. A super easy fix, watch. I mean, it's like a super easy fix. I'm just going to rewrite this like this. Am I allowed to do that? I mean, that is, if you think about what fractions do, right? If you multiply 2 fractions, if I take this fraction 1/4 and multiply it times sine x over x, when I multiply it across the top, I get sine x, yes. When I multiply it on the bottom, I get 4x. Yes, that's what that is, right? So all I basically did was I just peeled that 4 off to the side. And now when I take this limit, because there's multiplication, I can do the limit of each one of these separately. Why can I do them separately? We had the limit laws from last class that said if you had a product, you can do them individually. So let's look at them individually. If x goes to 0, does that have any impact on 1/4? No, no impact at all. So the 1/4 is still there. Okay, times, now when I take the limit of this one, as x goes to 0 of that, now do we have junk matching exactly? Are they both going to 0? Yes,
Yeah.
right? So where does that go? Where's it going? What's the limit of that then?
1.
1. So 1/4 times 1, our answer is 1/4. I realize that seems almost so trivial, sorry, that you just peeled the 4 off. It just seems like too easy almost, right? Doesn't that seem almost like too easy? Let me show you another one like that. How about pi x? Well, pi is just a number, right? Pi is just a number. So I could do the exact same thing on that one. I could rewrite as 1 over pi times sine x over x. And now again, you can do them individually. This goes to 1 over pi. And this goes to 1, so your answer is 1 over pi. Questions?
Yes, on the exam, are we gonna, when you said, hey, we should always plug in the limit before we do any algebra or anything, do we
Yep.
need to do that for every problem?
You at least need to do it mentally. You have to convince yourself it's 0 over 0. I mean,
Right.
there have been problems on tests in the past, tests that I've given where the problem, you do the limit, you plug in and you don't get 0 over 0. You
Right,
get like a number, right? Like 1/3, and then you're done. But students won't do that step. And then they start doing all this algebra when they never had to do anything, right? And
Right.
I always wind up catching the student on that. So I'm warning you, always run that step first, always. Now, I didn't do it here because, that goes to 0, that goes to 0, just by an observation. But you do need to think it through.
understood, thank you.
All right, you ready for the next one? Things seem pretty nice so far, don't they? Things seem pretty nice. Any questions on these? It's about to get weird as shit, okay? Here we go. Limit. Okay, let's go x go to 0 again. Let's not try and complicate this. Sine of 4x over x. That's not the first one I gave you, right? The first one I gave you was up here. It was sine of x over 4x. And we just said, oh, peel the 4 off to the side. And then you got it, sine x over x. Here, now I put the 4 inside, haven't I? Inside with the x. Yeah. You cannot pull that 4 out. You can't do that, right? That's not the way the sine function works. You can't just push scalars into trig functions, right? We have some certain like identities that can help us do things, but we can't do that. Please don't do that. So if I can't pull this 4 out, I can't get this 4 removed from this sign, then how am I going to get this to work if these don't match? You'll see what I'm saying?
You like put aside like sine of 4 and then sine x divided by x.
Okay, so can you do this like sine of 4 times sine of x?
And then like divide just the sine of x by x and then the sine of 4 by 1.
Got you. I understand what you're asking. No, you can't do that because we don't have a rule anywhere in pre-cal that said if you ever have like multiplication inside of a trig function, that you can split that into 2 trigs like that. There is no rule that says you can do that. Even if it's addition in here, well, if it's addition, I'll remind you. If you go back and look at your formulas for trig, here are the only real formulas we have for like, if you have sine of 2 things being added, you had this formula. Do those look familiar from pre-cal? These sum and difference formulas from pre-cal for sine and cosine. We have these, but, and then we have the double angle formulas. Those we have also, but see, it's sine of 2x, not sine of 4x. So it wouldn't necessarily work here. Understand? Like we can't do that.
Can we multiply both by 4?
Okay, so now okay, good. So can we multiply both by 4? What do you mean? Like when you say both, you mean top and bottom?
Yes.
Can we, everyone, or no? Are we allowed to? Can we multiply the top and bottom by 4?
Yes.
Yeah. Now, why would we want to do that?
So we could get 4 sine of 4x over 4x.
That's right. So Shams is saying, look, we really wish we had a 4x down there, right? We don't have a 4x down there. We wish we did, but we don't. So Shams said, okay, instead of doing you know, instead of hoping it was there, why don't we just force a 4 to be here? But the only way to force a 4 to be here is to put a 4 on the bottom and the top at the same time. And so if we do that, we can rewrite this as limit x goes to 0, sine of 4x. Now on the bottom, you have 4x, but then over here, you have 4 over 1. In other words, we just took this 4 that was under the 4 and slid it over here because it's multiplication. You're allowed to move things around like that. Very good. Now this, when we take the limit, now that goes to 1, right? And this one over here, well, it's a constant, so nothing happens to it, just stays 4. So your answer is 4. So we had to actually insert a 4 over 4 to make that work. You all understand? It's weird. It's going to get a little more strange. Here we go. All right. Let's let x go to 0. Okay, let x go to 0. If you let x go to 0, you get 0 in here and sine of 0, 0. On the bottom, you get 0 in here and sine of 0, 0. So we do get 0 over 0 here, right? So we do have a bad situation. But this also doesn't look like the ones we've been doing, right? Where it's just like sine of something, and then on the bottom, we try to get the x on the bottom to go away, right? We don't have that. Do y'all see that? So we are going to do something that's maybe it's going to look weird. I know it's going to look weird for a lot of you. Just do it, and then let's talk about it, all right? So first thing I'm going to do here is I'm going to peel this apart. I'm going to rewrite it like this. Now, all I need you to do is agree that that is the same thing, right? That is the same thing. I just kind of peeled the numerator off and made the numerator over 1, then peeled the denominator off and made 1 over the denominator. Now, if I do multiply those back together, it will give me the original problem, right? Right now, if I were to do the limit now, I would get 0 here, and on the bottom, it would be 1. What is 0 over 1? 0, right? 0 divided by 1 is 0. So this is not a problem, right? The fact that I get 0 over 1. The problem is here, because this goes to 1 and this goes to 0, right? So we have division by 0 right there. So this sine of 2x is a problem. That's what I'm trying to kind of make you see. This right here in blue is the problem. This is the reason we have this bad situation. Any questions? The blue is the issue. Now what I'm going to do is I'm going to be clever, all right? I'm going to be clever. And I'm going to use this whole idea of this sign junk stuff. If the junk matches and all that, I'm going to use that sort of property as leverage to be able to get this problem to work out. And remember, it goes either way, right? I can have the junk on top, sign and junk on the bottom. It doesn't matter which way I do it. So I am going to say, how can I make this better? What do we wish we had up here? What do we wish was up here?
2.
2, just
2x.
2? 2x, right? 2x. I really, really wish I had a 2x up there, right? That's what I would really like to see up there. So I'm going to make it appear. Here it comes. I can't just throw a 2x up there. The only thing I can do is 2x over 2x, right? I can multiply by that. Yes. And now that 2x, because this is multiplication, I'm free to slide it over here and put it on top. So let me rewrite. These limits always cause Cal 1 students problems because you've never really worked problems like this before. I'm gonna slide that 2x because you're having to like really think about how you are going to attack this. It's not like just follow the formula, plug in, you know. So here's what we've done. We realized we wish we had a 2x. We made a 2x over 2x appear. We slid the 2x on top. And now just kind of think about what's happening. Let's just think through it. This is headed where?
0.
0. Not undefined, right? It's headed to 0 because it's 0 over 1. This is headed where now when we do a limit?
1.
1. Okay, so that's no longer a problem, is it? Right? But shit, what about this? 1 over 0. It's undefined. Okay, so look, the way I like to think about this is, I don't know if you've ever heard this, like where you have a boat, right? That's sinking. It's got a hole in it, you know, and there's water coming in, the boat's sinking. So we basically had a sinking boat and we patched the hole here with the 2x. And we were like, oh, we plugged up the hole. And as soon as we plugged up that hole, we turned around and we realized we created a new hole. And so it's like we're trying to patch the holes, but every time we patch the hole, there's a new hole. That make any sense? It's like we fixed this problem, but created a new one. All right. So how are you going to fix it?
Can we do the same thing to the other one, the sign? Or no?
Can we, what do you mean? Can we do a 5x on the bottom here?
Yeah.
Now, yes, we can. But my question to you would be, why would you want to mess with this? Because this is not a problem, right? This one is not the problem. The problem is this one. Agreed, David? This one is the problem. This one is not causing us any issues. This is 0 divided by 1. That's okay. So do you understand, David? I'm saying this isn't a problem, but you're on the right track. David, the thing that's causing us the issue is that x right there, right? That's the x. That x, if it weren't there, causing the division by 0, then we'd be okay. So what if we take that x and slide it all the way under here, right to there? And then introduce a what? Because we have a sine 5x here. What would be good to have here?
5.
A 5x, right? Now we're going to
Yeah.
take the x from here, push it here, but then we need a 5. So I'm going to multiply the end of this by 5 over 5. And then
Yeah.
take that 5 and push it under here.
That fixes it.
And that fixes it. Let's see why it fixes it. If we rewrite this limit, we now have sine of 5x over 5x times 2x over sine 2x, and then times, let's see what's left here. The stuff in green I moved, right? Everything in green I moved to the left. That's this stuff. So I still have a 1/2, and I still have a 5 over 1, right? That's what I have. So let's see, Valerie, are you there?
Yes.
Okay, what do we got here? I know this is weird, but I'm just asking you, what can you tell me what each of these now do if we let x go to 0, where each of these are now headed?
They're headed to 1.
This one's headed to 1, right? Because you have sine of junk over junk. This one is junk over sine junk, so that's also headed to 1, right?
Yeah.
And then what about these two? X has no effect on them, right? So they just stay 1/2 and 5 over 1.
Yeah.
And now if you multiply all of those together, you get 5/2. And that's your limit.
Sir,
If this, yeah, go ahead, Shams.
I'm just confused on how did you move the x and the 5? Like, what property did you use to move them to the other fraction?
Okay, let me do this. If I asked you to put this all together, let's just rewrite the top. It would be sine 5x times 2x times 1 times 5 all over 1 times sine 2x times 2x times 5. Agreed?
Yes.
All right. All of these things are being multiplied together, right? All of those things are being multiplied together on the bottom.
Mhm.
Multiplication is what we call commutative. Commutative, I think I did that right. Commutative. In other words, A times B is equal to B times A. So whenever you have multiplication between things, you can slide them, move them around, right? So what I chose to do is move, like basically move this 5 out in front here instead of down here and put it here. But then when I rewrote it, I wrote it over like that.
Okay, it makes sense now that I see it all
And
together.
the X down here. Okay, good, good. Look, I'm sure if you have that question, people have that question. So I'm glad you asked it. We're using the commutative property of multiplication that you can slide things around. And when it comes to fractions, that means you can interchange the denominators however you want to do it, right? As long as there's multiplication between them.
Okay.
Weird problem, yes, weird problem. So here's what's going to happen. Someone's going to realize after they do a couple of homework problems that you could have got this answer 5/2 right in the beginning. If you just look at the 5 and the 2, that was our answer. On your exam, like if you get this problem and you give me the answer 5/2 and you don't have any work, I'm not going to give you any credit. Like this isn't about trying to find a pattern. This is about trying to understand how to introduce things, recognize where the problem is, where you're having issues. Let's do another one. Tangent 4x over sine x. You're going to need to know what tangent of 0 is, right? That goes to 0. Tangent of 0 is 0. And then the bottom goes to 0. So you have 0 of 0. This is bad. All right. Okay. So what did I do in the last problem? Let's see if we can kind of get our heads around what I did. I had 0 of 0 is bad. I had sine and sine here. So the first thing I did is I just rewrote it with the sine over 1 and then 1 over the denominator, right? That's what I did first. Let's just follow that same procedure. Let's do limit x goes to 0. Let's do tangent 4x over 1 times 1 over sine x. Right. I'm going to continue to kind of decompose this. I'm going to rewrite tangent using its definition. Tangent is sine over cosine. Right? That's the definition of tangent of something, sine over cosine. I'm going to continue to decompose this. I refer to this as I'm basically taking the expression, I'm just ripping it apart. Okay, like I'm tearing everything apart into pieces. So I'm going to write the sine of 4x over cosine of 4x broken down like this. Okay, you see how I did that? I just rewrote the sine 4x over cosine 4x, the sine 4x over 1 times 1 over cosine 4x, then I still have the 1 over sine x. So I've like ripped everything apart. Y'all see that? Just tore it all apart. Once I have it ripped all apart, I'm going to go look for where the problem is. And the problem right here is that I have a sine x, and that gives me division by 0. So Matthew, are you there? No, Matthew? Chloe, you there? I see you, Chloe. How are you doing, Chloe? Do you understand so far? I know this is weird, but are you kind of following?
Following.
Okay. Do you agree that this sign of X is a problem? Like it's causing division by 0?
Mhm.
So how could we fix it? What do we wish we had on top of this sign X?
An X.
An X. Okay, so let's make an X appear. So I'm going to multiply by what right here next to it?
X over X.
X over X. Okay, let's do it. X over X. Good. Now, Chloe, take the top X and let's just move it and let's drop it off here instead and get rid of it here, which would leave it with a 1. You there with me?
Yeah.
Okay, so now at this point, Chloe and everyone, we're recognizing that this first piece causes no issues. This is 0 over 1, no problem. 1 over, okay, cosine of 0, we didn't talk about this. I just assumed you knew this. Cosine of 0 is 1, right? Cosine of 0 is 1. So this is 1 over 1. That's not a problem. It was division by 0, but Chloe fixed it by putting an X on the top. So she patched that hole, but created a new one, right? Do y'all see that? We have 1 over X, and that's going to be division by 0 again. Got it? Understand we still have an issue? But that's okay, because Leonard's going to fix it. Where's Leonard? Yeah, Leonard, you going?
So just like last time, we're gonna move the X to the first fraction.
Over here, underneath the sine
Yes.
4x. Good.
Yes.
And that will almost get it, right?
Uh-huh.
What are you missing over there?
A 4.
How are you going to make that happen?
Multiply by 4 again.
Over here, by
Yes.
what?
4 over
By
4.
what? 4 over 4, right? 4 over 4. And then take that 4 on the bottom and push it under here. Get rid of it here. There we go. That fixes it. And now we just check to make sure we don't have any issues. When we take this limit, it goes to 1, right? We take this limit. Where does that limit go? Be careful. Cosine of 0 is 1. So that goes to 1 over 1. That's 1. And then Chloe fixed that one. That goes to 1 because we have junk over sine junk. We still have out here a 1 over 1. That's 1. And then out here we have a 4. So then you got a 4 back there. And so we multiply it all together. Our answer is 4. What do y'all think? Weird? Fun?
Very weird.
Very weird, right? Got a few more for you. Why don't I let you mess with these for a few minutes? See what you can come up with. 2 different problems here. Let's see if you can't maybe, stir something up on these. I'm going to go refill my drink while you're doing that. And then we'll talk about it. I don't want to take too much time, maybe 5 minutes, just see what you can get. It might help if you know what cotangent is, right? I'm gonna send out a quick poll. Just let me know if you've got them both done. If you don't yet, don't respond, but if you finish them, just put yes. So here it comes. While you're working them, I'm going to actually work them, and then you can see if you can follow what I'm doing. Okay, let's discuss. Both of these problems did not require that we came in and inserted something like we've done in the previous ones, right? In the previous problems, it's like, oh, I wish I had an X there. Oh, I'll make an X over X. Or, oh, I need a 4 there. Let's do a 4 over 4. These problems did not require that. All it required is that you were able to rewrite it in a way that you could see the jump over jump thing happening. So like on this first one, rewrite the cotangent as cosine over sine, rip the cosine and the sine apart, realize that this sine X down here gave us division by 0. So we wanted an X up here. So we just slid the X from here over. Does that make sense? Now, I know there might be someone in the class that got to this point, maybe, hold on. Maybe somebody in the class got to this point where you had an X here, cosine X here, and then you had 1 here. Did anybody do this? Introduce an X over X here? Anyone do that? Did anyone do x over x to get an x on top there? No. If you did, it actually still works because you can put this x here, right? And that fixes this. And then these two x's cancel. And so you're basically at the same spot.
I have
Now,
a
on the
question.
Yeah, question what?
I put 0, but I just want to know why it isn't 0. Like, because
Why what's not 0?
so
The answer?
yeah, because I put like 0 as x, and then cotangent. Is it like undefined or?
Yeah, it's undefined.
Oh, okay. So
Yeah.
if it's multiplied by an undefined, it cannot.
If you type this into your calculator, you're going to get 0 times undefined.
Okay.
So you have to rewrite it so that you can see you actually do have 0 over 0.
Okay.
Right.
Yeah.
This one's a little easier because sine of 0 is 0. So the top is 0, bottom 0. It's easier to see you have a bad situation here. And here you just rewrite the sine squared as sine times sine. And then you peel it apart into sine, and then 1 over t. Slide the t over underneath one of the sines. And then everything this one still goes to 0, right? Not 0 over 1. I mean, sorry, not 1 over 0, but 0 over 1, which is 0. And then this goes to the junk thing, that goes to 1, and then this goes to 1, and then you get 0. Because when you multiply, you get 0. Are there any questions on those two? So you have some problems in the book I'd like for you to make. I want to make sure that you do these. It's in 1.4. I really wish our book had more problems. I just want to make sure that you'll do them. Because I'll definitely ask problems like this on the test. It's 49 through 56. 49. So for 1.4, 49 through 56. Like I've said before, I mean, I recommend you do them all, but at least do the odds at a bare minimum. Okay, that wraps up 1.4. All right. 1.4 was all about calculating limits by hand. All right. The first part of 1.4 was like, hey, here's all the algebra, difference of squares, difference of cubes, conjugate, right? All these different things. And then this last part had to do with this special formula, sine junk over junk, and how we can use it to find some limits that otherwise we wouldn't be able to get. But it requires some weird stuff going on. All right. We move on. So I'm skipping 1.5. We will get back to 1.5. And the reason I'm skipping 1.5 is because it has to do with this concept called continuity. And the best way I can think about it is like right now we're on a road trip, okay? And continuity is like a pit stop to go eat lunch, all right? Could we do it? Yes, right? But the problem is if we do that pit stop right now, when we get back in the car to continue, we might just lose our rhythm, okay? I want to continue with limits, all right? Continuity is a detour from limits. I mean, it's still limits, but it's too much of a detour and I want to stay on the road, okay? That makes sense? There's nothing from 1.5, there's nothing from 1.5 that we need to do 1.6, right? So we can do it and then do 1.5 after. That means in your homework assignments, you're going to have to change things up because on your schedule, I believe I put 1.5 before, right? So instead, we're going to be doing 1.6 and then we'll get to 1.5 when we get to it, all right? All right, here we go. So 1.6, limits involving infinity is the name of the section. Limits involving infinity. So this section, 1.6, is split up into two parts. Okay, so 1.6 is basically part 1 and part 2. all right? They are both limits, both these sections within this section, both these parts deal with limits, but they're different. They're very different from one another. So what we're going to be focusing on right now is this right here, okay? This first part, and that first part is called infinite limits. Infinite limits. Now, just so you know, later on, the next section is going to be called limits at infinity. Okay, infinite limits and limits at infinity. Those are two different ideas. We are starting with infinite limits. Infinite limits. All right, so I'm going to try and motivate this with an idea. All right. Part of, I think, what makes calculus really hard for students is just this basic understanding of like a number sense when it comes to fractions. All right. So let's just say I give you a fraction. All right. Here, a numerator and a denominator. All right. Let's just talk about the behavior of fractions. What if I tell you that this number on top is really, really small? Okay, a really, really small number. By me just telling you that, is there any way you can tell me about the answer, whether or not it's a small or a big number? If I just tell you what the numerator is that enough for you to tell me, oh yeah, if the numerator is really small, then yeah, the answer's got to be small? Is that enough, or do you also have to know the denominator?
You have to know the denominator.
You got to know them both. Okay, you've got to know them both. You have to, because if I say this is small, this could be even smaller. So we have to know them both. But if I tell you this, what if I tell you that the numerator is small and the denominator is large? And I should have said this before I started this. When I say small in this class, what do you think I mean?
Relative.
Small, but like, I mean close to zero. Like a number that's really close to zero is what I mean by small. The reason I say this is because when you're learning about the number line, right? If I were to ask you to compare -2 to 1, which one is smaller? Well, on a number line, the numbers to the left are smaller, aren't they? So -2 would be smaller than 1 on a number line. But when I'm talking about small in here, what I mean are numbers that are close to 0. So I just want to make sure we're talking, when I'm using this language of small, you understand, I don't mean numbers that are way out here to the left small. I mean numbers that are, if you take their absolute value, it's a really, really tiny number close to 0. Okay. So when I say this numerator is small, I mean a really, really like 0.00005 or something like that. So if I take a very small number and I divide it by a very large number, what's that answer going to be? Can you tell me? Is it big or is it little? What do you think?
Little.
I'm sorry, Nico?
Small.
Small. It's small. Does everyone understand that? If you take a small number and divide it by a big number, it gets even smaller, right? So this is going to be very small. What if I do it the other way around? What if I take a fraction and I say this is large, right? A large number, and this is a small number. Do you know what the answer is going to be?
Bigger.
It's going to be big, right? It's going to be a really big number. Now that may seem, I don't know, you may be thinking about that and be like, oh yeah, duh, I know that, or I don't know what you're thinking, but this is a concept that everyone has to understand to be able to do what we're about to do. So if you got small on top, big on the bottom, that's small. You have big on the top, small on the bottom, that's big. Let's say that again. Small on top, big on bottom, small. Big on top, small on bottom, big. Yes? We understand? We understand? Okay, so how about this? Limit x goes to 0 of 1 over x squared. All right, so I don't want to keep on saying Red told us so, but Red did say last class, what's the first step of doing a limit, right? And it's always to try and plug 0 in, right? So what happens right now if I try and plug 0 in for x? Tell me what I get.
Undefined.
It's undefined. Okay, I agree. It's undefined. Now, are you getting 0 over 0?
No.
No, right? You're actually going to get 1 over 0. What I've told you up to this point, what I've told you, and all I've told you is that, and I showed this to you last time, that if you see 0 over 0, you're going to do some algebra, some trick, right? That's what I told you. 0 over 0 algebra trick. I didn't tell you what to do if you get 1 over 0, did I? I didn't. I did not tell you what to do. But let's think about what's happening here, all right? Your numerator, 1, well, let me do it this way. Your numerator is a fixed number, isn't it? The number 1. I didn't spell fixed right. Your numerator is a fixed number, yes? It's not moving, it's not changing. But your denominator is doing what? Well, it's headed to 0, isn't it? Isn't it headed to 0? And because it's squared, it's always a positive number. Do you agree with that? Like no matter what, if you start plugging in numbers close to 0, you know, from both sides, remember you always have to approach that limit from both sides. So if I'm approaching 0 from either side, it's a very small number, right? It's a very small number, and then I'm squaring it, which makes it positive. So it doesn't matter if it was on the left or right. Would you agree that this is going to be a very small positive number? Yes? So what should happen if the number on top doesn't change, but your denominator starts to get smaller and smaller and smaller and smaller and smaller and smaller? What is this ratio going to do?
Get bigger.
Bigger or smaller? Enrique?
It'll get bigger.
It's going to get bigger, right? It's going to get bigger and bigger and bigger. The smaller the bottom gets, right? The smaller it gets, the bigger the fraction becomes. And so this thing should be headed to what? Well, the top was a fixed number, right? It was the number 1. It was a positive number. Y'all agree? The top was a positive fixed number. And the denominator is a very small positive number. Our answer should be a positive number, but it should be like getting bigger and bigger and bigger, actually getting infinitely big. So it should be headed towards infinity, positive infinity. Now let's look at a graph, okay? I think if we look at the graph of 1 over x squared, you'll be able to buy into this easily. I didn't want to just show you the graph because I wanted you to think about it in the sense of numbers. 1 over x squared. There's a graph of 1 over x squared, right? If we are approaching 0, right? If I'm approaching 0 from the left and from the right, where's the function headed? Up and up and up and up and up and up and up, and it keeps going, doesn't it? In fact, I could scale this out so you could see, doesn't matter how far I go here, right? It's just going to keep taking off to infinity. It's like a volcano, like an infinite volcano. So as you come in from either side, your function's headed up towards infinity. Does that make sense? Yeah? So the answer to this, limit as x approaches 0 of 1 over x squared. This is the first time we've ever had this as an answer. The answer is infinity. And there was no algebra. There was no trick. There was no sign junk over junk. It was purely me thinking about what's happening. Fixed number on top that was positive, divided by a number on the bottom that's getting small, and it's always positive because of the squared. Let's try another one. How about this one? Limit x approaches 0 of 1 over x. So I started with 1 over x squared. I did that intentionally because 1 over x is actually harder than 1 over x squared. Let's think about why. So we plug in first. Okay, we plug in, we get 1 over 0, right? We get 1 over 0. Okay, that's not the 0 over 0 bad algebra thing. This is, we need to now think about what's happening, all right? The numerator is fixed, right? And it's positive, yes? Numerator's not moving, it's the number 1. The denominator, though, is small, right? It's getting smaller and smaller, but see, we're approaching 0 from which side? Well, if I don't put a plus or minus, you have to approach from both, don't you? So what happens if I approach from the left side? Are these small negative numbers or positive numbers? If I approach from the left.
Positive.
Negative.
If I come in from the left side of 0, right? From the left side of 0, I'm going to have very, very small negative numbers, right? So what happens if you take a positive number that's not changing and you divide it by a negative number that's getting smaller and smaller and smaller? That should get big, but negative, right? It should be a huge negative number. But if you come in from the other side, the right side, now your denominator is small but positive. Do y'all see that it's like there's conflicting ideas happening here? From one side, you're getting really, really big negative numbers, but from the other side, you're getting really, really big positive numbers. Let's look at the graph. That is the graph of 1 over x. You should recognize that from college algebra. And look, you can see this happening. If we come in from the right, approaching 0, the function is headed where? Up and up and up to positive infinity, right? But if we come in from the left-hand side, now our function is headed down, down, down to negative infinity, right? Do y'all see the difference there? What happened when we were doing limits a few days ago? We said that when you do a limit, that in order for the limit to exist, the left and right hand sides had to be going to the same thing, didn't they? On this graph, are the left and right going to the same place?
No.
No, one of them is going to positive infinity, the other one's going to negative. So what do you think my answer is going to be here for this problem?
Does not exist.
It does not exist. So the limit as x approaches 0 of 1 over x does not exist. Now I'm going to illustrate again why that is the case. Why? Because if you take the limit as x approaches 0 from the left, notice I put the negative sign there. From the left of this, you get a fixed positive over something that's small but negative. And so your ratio of a positive and negative number should be negatively huge, right? Fixed on top, bottom's getting smaller and smaller and smaller. That's going to give you a negative number. But if you come in from the other side, running out of time, then you get a fixed positive number over a small number, but this time it's positive because you're coming in from the right-hand side of 0, and that should be a very, very big positive number. That's why this limit didn't exist. The left-hand limit does exist. So if you want to know what the left-hand limit is, that's what it is. If you want to know what the right-hand limit is, the answer is infinity. But the limit itself from the left and right doesn't exist. So it is possible now to have an answer to a limit problem be infinity or negative infinity. That is a possible answer we can get now. And that's why this section is called called infinite limits. We can get answers that are infinite. All right, now I had not done enough for you to go do homework on this. There's still a lot more for me to talk about with this. So we are just barely going to creep into 1.6 the next time we meet. So for the weekend, you really want to focus on making sure you've got all of 1.4 done. If you did all the odds, go back and do the evens. If you really want to, if you got nothing else to do and you want to practice, I would recommend going to the chapter review for chapter 1 and looking at like problems, where are they? 21 through 30. Chapter review 21 through 30. If you're really like desperate to get more practice with these limits, chapter review 21 through 30 would give you, you know what, hold on. Take that back. Okay, 21 through 30, but you can't do 28. 28 you're not ready for. Yeah, so, all right. Any questions? We're out of time. I don't know, time goes by. I've noticed this, what, 2 years of Zoom we've been doing basically, it's Zoom is slower than a normal class. Like a normal class, I just seem to work, I go faster. So we are where we are. We lost a day. We'll do our best. Any
Just to
questions?
clarify, you said 21 to 30?
If you're looking for more practice, the chapter review 21 through 30, but you probably want to avoid number 28.
Okay.
Yeah, 28 looks like it would be a problem. Yeah, it looks like that's the only one you would have an issue with. Yeah.
Professor, those OneNote notes, where can we find them?
The what?
The notes that you just like, these notes. The screen.
These right here?
No, the written ones. Can we find them?
Oh, these right here.
Yeah.
The ones I'm writing?
Mhm.
I was waiting for somebody to ask, actually. I was waiting for someone to ask. Yeah, so what I'll do is I will send the class a link to a OneDrive folder. And then from here on out, at the end of class, I'll upload the handwritten notes.
Okay.
I literally have been waiting for someone to ask. I do it for all my classes. I just wait for someone to actually ask for them. So I'm glad you did.
Okay.
So I will send that out and you'll have a link to it and I will upload all the notes I've had. Now you have to kind of keep in mind some things here. I have 3 programs running. I have my OneNote, which is where I write down my notes, but I'm also using a screen write program where I can write on my screen. That won't be in the notes.
Okay.
So I just want you to realize that there are certain things that I do in class that will only be on the video.
Yes.
Yeah, okay.
I just needed the other ones too.
Yes, I'll send that out to you.
Thank you.
All right, anything else?
For the homework for 1.4, you said, we should do 1.4 as review, but what's due is just 11 through 28, right? Or all of them?
I think someone asked me that earlier, right? For 1.4, the 11 through 28, absolutely you need to do. Okay, like those are like, that's the heart of the class of that section. But then also the 49 through 56.
Yes.
That I just gave today. Yeah. That would be, you can ignore what's on the schedule. If you just do those, you're good.
Got it. Thank you.
When I go to make a test, I'm going to pull problems from 11 through 28, those types of problems, and then 49 through 56, those types of problems. Everything else in that section, I don't really care about.
Perfect. Thank you.
Yeah. Mm-hmm.
And also we turn in the 1.3 little exercises as well before Monday.
Yes, the 1.3 homework is due with that 1.4. Okay,
Okay, thank you.
thank you. Y'all have a good
Bye, have a
weekend.
great weekend.
If I don't
Thank
see you in
you.
office hours,
Have a good weekend, sir.
you as well.